All right, so today we'll be discussing limits and continuity. What I had planned to do is I have a whole lot of information in the Canvas course. Okay, you may notice there's the learning material that I put up in the front part of each module, and then there's supplementary material. What that supplementary material is are notes from a previous calculus course that I taught. They're usually a lot more detailed than, say, the text that's in this course. What I'd like to do is I'd like to try to use the simpler text that's in this course and see if that's enough. And we can always supplement it if it's not, okay? Rather than doing overkill, I'd like to start small and then work my way up if people need more examples, more review. So what I'm planning to do today is use our Creative Commons, our open text, to introduce the topic of limits and continuity. And then I'd like to do a bunch of examples with you, okay? Because I find that that's really the best way to get the concept clear in your mind. I mean, we can sit here and read about it forever, but until we actually try it, not too helpful, right? Okay, so let me share my screen with you. Again, this sometimes takes a while, so please be patient. Let's see. It is slow this morning, so I will get there, I promise. Alrighty. So I am going to okay, so what I have going on here is the text that's in your module 2, okay, for limits and continuity, okay? And like I said last time, the idea of a limit is really helpful when we're talking about calculus operations, okay? So we were talking last time about the difference between an average rate of change between 2 points on a graph, right, which is the slope of the secant line between those 2 points, and an instantaneous rate of change at a single particular point. Well, actually, when those 2 points get as close as you want them to be without being the same, okay? So that interval that gets smaller and smaller between the 2 points, okay, is something that we can address with the idea of a limit, okay? So that's kind of why we're talking about limits, okay? Because it's going to help us calculate the instantaneous rate of change without building a whole lot of tables and graphs and things like that, okay? So if we take a look over here, we have this tiny little figure 1 graph, and you can see it's kind of got a hole in it, all right? The x value c here, okay, on the horizontal axis, gives us an idea of, well, we can move along the red line, okay, towards this x value c, okay, and if we do it from the left-hand side, you can see the y value gets closer and closer to the value L, okay? Likewise, if we move closer and closer to this x value c from the right-hand side, you can see that the y value is getting also closer and closer to the value L, okay? Now, what's important to realize is it doesn't matter what happens right at the value x equals c, because you can tell in this graph, okay, the value of the function's not defined there. There's a hole there. Okay, but the fact that the value at x equals c isn't defined doesn't mean you can't have a limit, right? Because my y values are getting closer to L as I come at c from the left and I come at c from the right, then that limit exists, okay? We could say the limit of f of x as x approaches c is L, okay? So here's the way we talk about limit. So the difference, I mean, you're all familiar with a function value at a given x, okay? What's important to understand with limits is they're not the same thing. Limits are asking you what's happening in the neighborhood of x equals c, not right there. Okay, so it's possible to have an undefined value right at c, but the function is totally well behaved as you get near c from both sides. Okay, the arrow symbol in the limit notation, okay, here's the mathematical notation for a limit, okay? You would read this exactly as the words are up here. The limit of f of x as x approaches c is L, okay? That's exactly the way you read it, okay? So approaches means gets arbitrarily close to, okay? You may have seen, those of you who haven't seen limits before, you've seen the concept before when you're talking about a graph approaching an asymptote, okay? If you remember from college algebra, when you have a rational function graph and it has a horizontal asymptote, as x gets very, very large, you can see the y values of that graph getting closer and closer and closer to some horizontal line, but it never reaches it. Okay, that's the idea of a limit. Okay, how close do you want to get to that y value? I don't know. Pick an x value way out there and we can get as close as you want. Okay, so is everybody all right with the general idea of a limit? Okay, so okay with the general idea of a limit. Okay with the general idea of a limit. For those of you who may have actually been in a calculus class before and you might remember epsilon delta descriptions, we're not going to do that. Okay, we're not going to do that in this class. Okay, really all I need you to be able to do is understand the concept of a limit and be able to tell me what the limit of a function is looking at a graph at a certain x value, or looking at a table, or more advanced, looking at a symbolic rule, but you know, you can always graph those, right? Okay, so that's pretty much what we're going to be doing. We're not going to be doing any epsilon delta definitions, for those of you who know what that means, okay? So going forward, okay, let's talk about the distinctions here. F of c, okay, f of c is a number that describes the behavior of the function at the point c. In this graph up here, there is no value, okay? That's what the hole means. The value of f of x at c is undefined, okay? But normally, if you're looking at a graph without a hole in it, there's a certain y value there, okay? The limit as x approaches c of f of x is a number, if it exists, that describes the behavior near but not at the function value at x equals c. Okay, so as we get close, but we're not there. Next, if you have a graph, it's pretty easy to determine. Okay, so here's a graph, and you can see this is kind of a graph that looks like somebody ran it through a lawnmower. Okay, it's got holes in it, it's got chops in it. Okay, and we'll use the idea here, okay, when we talk about continuity, okay, what it means to be continuous. We're not quite there yet, okay? So let's look at each of these pieces. The limit as x approaches 1, okay, and you have to look at how you approach the x value from both sides. You can't just look in one direction, okay? So let's take a look here. Here's x equals 1. And you can see there's nothing weird about the graph here at all, okay? There's a filled in circle here, which means the graph is defined at that value, okay? So as I come riding along the graph from the left, okay, and I approach x equals 1, okay, what y value do I get close to? Okay, anybody want to type it in the chat? So as x approaches 1, what y value am I getting close to? Okay, you can see right here, and some of you I'm sure are looking at this and saying, duh, Okay, the value at x equals 1 is 2, so that must be the value I'm getting close to, and you're absolutely right. Okay, this is a graph where the limit and the function value are the same. Okay, you can see as I approach x equals 1 from the left, I'm also getting close to the y value too. Okay, so that's 2. The fact that the value of the function at 1 is 2 is, as they say here, is irrelevant to the limit. Okay, that's a nice to have, and it's important for continuity, okay, which we're talking about next. But as far as the limit, you can have a limit without a function value, okay, like we did in this graph up here, right? Got a limit, it's L, function value doesn't exist. Okay, let's look at B. As x approaches 2, what's the limit of f of x? Well, again, right on the graph from the left, as you get close to 2, you can see that value is getting closer and closer to 3, right? And as I write on the graph from the right towards x equals 2, you can see the graph's getting closer and closer to 3. So the limit as x approaches 2, okay, is 3. Even though the value right at 2 of the function, f of 2, as they say down here, is undefined. Okay? So this second one, part B, is an example of where the limit exists, right? And it's a number, 3, okay? But the actual function value at that x is not defined. Okay, that's like our figure 1 example. Okay? So you can see holes in graphs, typically the limit exists there, even if the function value doesn't. Okay? Let's take a look at C. Okay, the limit as x approaches 3. Okay, I'm going to let you do this one. Okay, and I'll bring up the chat. Okay, and I'll ask you, what is the limit as x approaches 3? Okay, we're getting some values. Okay, remember you've got to check from both sides. All right, so again, the y values are approaching 1. You're absolutely right. Okay, so what is f of 3? Is it the same number? No, you can tell it's not. It's this 2, this dot up here. Okay, this sort of a situation occurs a lot of times in piecewise functions where you've got like an exception to the rule, okay, and you've got part of the function that's defined one way and part of the function that's defined another way. We'll look at piecewise functions when we do a worksheet together, all right, and I'll even show you, how to graph with a restricted domain in Desmos, okay, so hopefully we can do some graphing in Desmos to see that. So that's a good one, okay? So here the function isn't undefined at 3, it just has a value that's not the same as the limit. Again, that's not important for finding a limit, but it will be for determining continuity. The last one, okay, how about this? What's the limit as x approaches 4? Okay, you try this one. Okay, remember, you've got to look from both sides. All righty. Okay, for those of you who haven't seen limits before, if you're a little confused, that's okay, because this is weird. Okay, let's take a look. If I ride the graph from the left and I try to approach x equals 4, I'm getting closer and closer to the value 2. Okay, so as I approach from the left, I'm getting closer to 2. As I approach the graph from the right, though, I'm getting closer to 3. Since the two values don't match, okay, we say the limit doesn't exist. Okay, so the values from either side must be the same for the limit to exist. Okay, so in other words, you can't say 2-3, depending, okay? The limit as you approach it from the left is 2. The limit as you approach it from the right is 3. You can say that. But the limit as you approach x equals 4 doesn't exist because you're getting two different conflicting pieces of information. Okay? Okay, and how about f of 4? What's that? What's f of 4? Yeah, f of 4 isn't what either of those left or right-hand side limits are, right? Okay, so the function value, okay, isn't either the left or right-hand side limit. It's certainly not the limit as x approaches 4. So you can see these things can tell you a whole bunch of different pieces of information. Okay, everybody okay with that? Okay so far? All right, again, if you've got any issues with what we're saying or what we're doing, please shout out, okay? And we can ask questions. You can even unmute yourself, ask a question. Okay, that the main thing is stop the train if it's not clear. Okay, we can always go over bits. Let's do a little bit more work, okay, with tables. We've done this, okay, so we don't have to do that. Let's take a look at how you can. It's easy with a graph, as usual. You can tell what things are getting close to looking at a graph. You just have to recall on some graphing calculators, whether it's Desmos or whether it's your TI-84. It might be difficult to see holes, okay? So you have to be a little careful of those. Click on the point and see if you've got a y value. That's the best way to determine if a function's defined at a particular point. But let's talk about using algebra and using tables, because like I said earlier in our course, the graphs, the tables, and the algebra should all give you the same information. Okay? So here we have a limit statement. They want to know the limit as x approaches 1 of this rational function. Okay, so hopefully everybody recognizes this as a rational function. And you also realize, well, wait a minute, if I put 1 in for x over here, I'm going to make my denominator 0, okay? So I can't actually do that, okay? So one thing you can do, okay, you can, of course, graph it. Some of you might be comfortable with factoring the numerator, okay, to see if you share any factors on the top and the bottom. Just a quick refresh for rational functions. If you share a factor in the numerator and denominator, that x value is going to give you a whole, right? If you don't share a factor in the numerator and denominator, anything in the denominator, any factor down there, gives you a vertical asymptote, okay? Just a refresher. But what they're doing here is they're going to try to evaluate the function and see what happens as they get close, okay? So what they've done is, let me just bring up my TI-84. And again, I realize that some of you don't have a TI-84, but let me just bring that up briefly just to show you. Okay, here's how you would do it. Okay, you would put that function in y equals, okay, and I'm going to put it in there with a fraction. So alpha y equals numerator denominator. Okay, that way I don't have to worry about parentheses. And I'm going to type 2x squared, what is it, minus x minus 1 on top. And then in the denominator, I have x minus 1. Okay, and again, you can do this in Desmos as well. Okay, but again, I'm kind of just showing you how you would do it on a TI. And again, I'm not necessarily interested in the graph of it. Okay, it turns out the top does factor into 2x plus 1 times x minus 1. So I know I would have a whole at x equals 1. Okay, if you graph something like this, it's going to graph as a straight line, okay, which is kind of disturbing because it makes it look linear. But what I want to show you is the table, okay? So first I'm going to go to table settings, so second window, all right? And I want to set my independent, my x variable to ask, because I want to type in numbers, right? And then I'm going to go to table, second graph, all right? And you'll notice it's asking me to type in x values, okay? So I want to know what happens as I get close to x equals 1, okay, from the left. Okay, well, what number is close to that? Well, how about 0.9? That's pretty close, okay, but it's not quite to 1. And you can see my y value is 2.8 there. So I'm going to get closer than that. I'm going to get closer by saying 0.99. 0.999. Okay. All right, now what happened here is my calculator is rounding. Okay, let me show you. Okay, it's not really 3. Okay, my calculator is rounding. So it's important if you're using a TI-84 and you're looking at table, actually highlight the cell you're looking at. Okay, and you'll see we're not quite there. Okay, so 3 is the limits of rounding in the calculator. This is why calculators are approximation values, okay? And your calculator isn't doing algebra here, it's doing some sort of numerical analysis, right? But it's an approximate value, okay? So let me clear this one out because it's kind of delete it, I can't delete it. Let's type over it. Let me get exactly to 1, and I get an error. Because what happened? I fell into the hole that's in the function. The function isn't defined at x equals 1. So it gives me an error saying there is no output value, right? Now let me get close to 1 from the other side. How would you do that? Well, you'd get beyond 1, say at 1.1, and you'd come down 1.01, 1.001. Okay, and you can see here I'm getting close to 3 from the left. Here I'm getting close to 3 from the right. Okay, so this is the way you can use a table, okay, like in a graphing calculator, to show you what you're getting close to. Okay, is everybody okay with the table? Again, I wanted to show you how they got the values they're showing you in the text. Everybody okay with the table? I'm sure, again, a lot of you have done this before. This is particularly useful when you have exponential radical functions, like a logistic function. Okay, I'll show you one of those in the examples. Okay, this turns out to be really a really handy method. Okay. Okay, so here we are. And you can see again the tables, all right? As x approaches 1 from the left, f of x is getting close to 3. As x approaches x from the right, from the high side on down, you can also see f of x is getting close to 3. Okay. Now the function isn't defined when x is 1 because that's where the hole is, but when we're close, the values are getting close. Okay, so we can say the limit as x approaches 1 is equal to 3. Okay. Algebraically speaking, okay, if you didn't want to mess with the table, you can do something that they've told you not to do at all when you're in college algebra. You could factor your numerator. Okay, and guys, there are factoring apps out there that you can put a quadratic or a polynomial in, and if it's factorable, it'll factor it for you. Okay, so look for those. Okay, Symbolab is one of those. Okay, so basically here's the factored numerator, and you can see, hey, common factor. Now they told you in college algebra, don't cross it out. Okay, well, you don't want to cross it out unless you're aware of the fact your function isn't defined when x is 1. Okay, so you can cancel out the x minus 1 factor as long as you say this value is equal to 2x plus 1 as long as x is not equal to 1, which says that you can plug in any other x value as long as it's not 1. Okay, and you can see as you get closer and closer here, right? If you were to say, well, suppose I'm just really close to 1, but not quite 1. What am I close to? Well, this will be 2 times something a little less than 1 plus 1. It's really close to 3, all right? And if you plug in an x value that's slightly larger than 1, this would be a little bit more than 2 plus 1, so a little bit more than 3. So you can see, okay, that your f of x value is near 3 as long as you're on either side of x equals 1. Okay, so that's how you would handle it algebraically, right? Graphically speaking, again, this is the way it would graph, okay? Because again, the way the function interprets this, it's not linear, okay? It's actually a rational function with a hole in it, okay? And so basically what you would need to do in a graph, if I go back to my TI-84, which you should still be able to see, let's go zoom 6 so I get it on a normal window. Okay, it looks linear, right? But you know it's not linear, right? We plugged it in over here and you can see it's for sure, it's rational. So again, look at x equals 1. Plug in that x value and see what the y value is. Here's how you do it on a TI. Second, trace, use the value function, plug in 1. And notice down here, you get y equals nothing. That's because it's not defined there, okay? If you were to zoom in very far on the graph, you might be able to see a tiny little break in the blue line, okay? But this is the most reliable way to find holes with a graphing calculator, is actually ask the graphing calculator, what's the y value when x is 1? And it'll say, there isn't any, okay? All right, so basically you can see here are a bunch of different ways to evaluate a limit, okay? So everybody okay with the table, the algebra, and the graphical way to evaluate a limit? Okay, everybody all right with the 3 ways? Now, some of these methods, okay, might require you to dust off some of your algebra skills, okay? Particularly if you're dealing with, say, a square root. You might have to remember how to rationalize a denominator, remember that, in order to be able to plug in the value of x that you're trying to find the limit at. But again, remember the graph and the table should tell you the same thing as the algebra, okay? All right, I have a request to go over the graph again. So I'm doing it on the TI-84. Okay, so here is the graph. You can see it right up here. Here's what I have in Y1. I have the rational function. And what I did was I said, well, it looks linear, but I know I didn't graph a linear function. I graphed a rational function. Okay, and from what I studied in college algebra about rational functions, I know the function isn't defined at any x value that makes the denominator 0. So I know if I plug a 1 in here for x, I'm going to get a divide by 0 condition, which makes the function undefined. So how would I see that on the graph? I'm going to ask the graph, what's the y value when x is 1? Here's how I did it. Second, trace, that's my calc menu. And the very first one is as value. What that says is give me an X value, I'll tell you what Y is. So I'm entering it. Okay, and I want to know what is the Y value when X is 1. And the calculator gives me Y equals nothing. Okay, not at all, nothing. Okay, so this is how it looks on a TI. Would anybody care to see it on Desmos? Okay, want to see Desmos? Since again, I'm assuming the majority of you don't have a TI-84 handy. Okay, so let me show you Desmos. Okay, great. I will need to, give me a moment, open Desmos, and then I need to share my browser with you. So again, technical difficulties in the background. So sharing another application, which should be my web browser. Okay, everybody able to see Desmos? Okay. Oh, what I did on the graphing calculator, the TI-84 window, I did a zoom standard. Okay, so 10 by 10. So -10, +10 for both X. Okay, that was on the TI-84. Again, one thing I love about Desmos is I don't need to mess with windows, right? I've got pinch and zoom. So up here, I'm going to say Y equals, okay, and I am going to type in my polynomial. So hopefully, I want to see how smart Desmos is. So 2x squared minus x minus 1. Let's see if it knows enough to, nope. Okay, so here's the trick with Desmos. Okay, you need to be able to either create a fraction. I'm trying to see if there is a way in the template to create a fraction. I'm not seeing one. Okay, so you are stuck in Desmos, it looks like, with remembering, parenthesize the numerator, 2x squared, right? Minus x minus 1, that's my numerator. And then I'm dividing it by my denominator, which is x minus 1. Okay, once it gives you the fraction bar, you technically don't need the parentheses downstairs, but it's a good idea to put them there anyway. Okay, so again, remember, if you're graphing in Desmos, make sure it looks like what you expect, right? I want the whole polynomial in the numerator and the whole polynomial in the denominator, okay? And now again, it's showing me intercepts, but I want to know what's happening in this graph when x is 1. Okay, so I find x is 1, and again, I can zoom in if I want. Okay, and it gives me 1. I can pull this down, and then I have to click right here. Okay, everybody see undefined? Okay, so there's my little hole in the graph. Okay, now this is assuming you remember some stuff from college algebra, and you remember 1 will make that denominator undefined. Okay, so everybody good with Desmos? Okay, everybody okay with this? All right, let me go back to sharing my the Acrobat here, my notes. Okay, now what we've done, what I told you to do when you were finding limits, remember I told you approach the x value from the left and from the right in order to determine if the limit exists. These are called one-sided limits, okay? A left-hand limit if you're approaching from the negative side, and a right-handed limit if you're approaching from the positive side. And here's kind of the example they use to motivate the discussion. What happens to us at a place depends on the direction we use to approach the place. If you come at Niagara Falls, which is a large waterfall in upstate New York, it's between the New York and Canadian border. If you approach it from the upstream side, then you're 182 feet higher, okay? And you have different worries than if you're approaching it from the downstream side. In other words, what they're saying is if you're coming down the Niagara River toward the falls, okay, you're 180 feet above sea level, and you're going to be worried about going over the falls, okay? If you're approaching the falls from the downstream side, you're 182 feet lower than the top of the falls, and you're more worried about the spray and the water that's going to hit you coming over the falls, okay? So the values of a function near a point depend on the direction that you use to approach the point, okay? And we saw that in one example we looked at back here, if you remember, way back here, this last one. When we approached x equals 4 from the left, we got one value of a limit 2, and when we approached it from the right, we got another value for the limit 3, because there's a break in the function right there at 4, okay? So it's important to pay attention to what direction you're looking at, okay? So here's the left hand and right hand limits. This is a notational thing, okay? So I just want to make sure you understand the notation here, okay? The left hand limit, as you approach, as x gets close to c of a function, okay, is L if the values of f of x get close to L as you get close to c on the left. Now take a look. The limit as x approaches c from the left. Everybody see that little negative sign that's written as a superscript? That means you're approaching c from the left hand or the negative part of the x-axis, okay? From the left means you're going from negative towards positive, okay? The right-hand limit, okay, has a little plus sign there, okay, as a superscript, okay? And what that says is you're approaching this x value, c, from the positive side of the x-axis, okay? So from larger values on down, okay? Is everybody all right with the notation? Okay, notation okay? And like I told you before, the right and left limit must be equal at a given x value in order for the limit to exist. Okay, so I'm going to put that in the chat. The right and left limits at x equals c must be the same number for the limit as x approaches c2. Okay, so basically I can't have that situation I had before as x approached 4 where I get two different values. Okay, so that's basically one difference. Okay, another thing that you might be interested in is, what do you think happens, okay, as we've talked about rational functions with holes, but what about a vertical asymptote? Okay, so if a function, let's say, if f of x has a vertical asymptote at x equals 3, does the limit as x approaches 3 exist? And then why or why not? This is a question I'm putting in the chat for you, okay? So suppose I have a rational function and it's got a vertical asymptote at x equals 3. You remember what happens to functions at asymptotes? So do you think the limit exists there at x equals, as x approaches 3? Okay, if you think the limit exists, you have to tell me what the value of the limit is. Okay, so we're getting some different answers from people, which is exactly what I was hoping. Okay, so some people say yes, some people say no. Let's take a look at Desmos. Okay, and I will put in a different function. This is a function that has a hole in it. I'm going to change the denominator, okay, to this. No, let me not do that. Let me change the function entirely. I'll make it a simpler function. Okay, so let me zoom out a bit so you can see it. This looks more like your traditional rational function. Okay, all right. And I said, what happens as x gets closer and closer to 3? Now take a look at my function rule, okay? There are no shared factors in the numerator or denominator, so this function has no holes in it. Holes come from shared factors, okay? I have x equals -1 in my numerator, okay? Which it turns out gives me my vertical, my horizontal intercept, my x-intercept, okay? There's my 1, okay? And then this, okay, is a vertical asymptote, okay? Let me see if it will let me graph that value, okay? You can see the blue line is my vertical asymptote, yes? All right, and now what I need you to do is approach x equals 3 from the left. Okay, let's take a look at some of my y values. I'm going to ride down in the graph. Okay, I'm getting closer and closer and closer and closer. Okay, I'm going to zoom out a bit. What's happening to the y values as I move down this part of the graph? Can anybody tell me what's happening to the y values? Okay, they're heading towards negative infinity. They're getting larger and larger and larger. They're not approaching a value. Okay, how about as I get closer and closer to the blue line this way? What's happening to your y values here? Okay, positive infinity. So basically, your y values in your graph are not approaching a number. They're not getting closer and closer to a given number. They're shooting off to negative and positive infinity. So if the y values don't get close to a number, but get larger or smaller, the expression is without bound. That means they're not getting close to a number. They're just growing, growing, growing. Or in the case of this arm, they're going down, 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 down. Okay? Then the limit as x approaches 3 does not exist. Okay? So basically, in order to have a limit, okay, you've got to be approaching a number with your y values. Okay, infinity isn't a number. Okay, so you're heading off and your values are growing or they're getting more and more negative. Limit doesn't exist. And the other criterion is as you approach your x value from either side, you've got to be approaching the same number as your y value. Okay, so here you can see an example of a vertical asymptote, okay, giving rise to no limit here, okay, and that's exactly what it means for your y values to increase forever, is there's no limit to them, right? Same thing down here. They're getting more and more and more negative without a limit, okay? Is this clear? Okay, is this topic clear, the idea of what happens at a vertical asymptote? Make sense? Okay, awesome. Let's just take a little bit more of a quick look. Okay. I want to kind of move to what we've been sharing with. I want to share the kind of worksheet that we're doing. Okay, so what I'm going to be doing is probably trying to share my tablet with you. Let's see if I can do that. Okay, and these are in your Canvas class as limit and continuity note worksheets, or worksheets at the bottom. Okay, so again, I'm trying to get the technology to collaborate with me. Okay, hang on. And again, if we do parts of these together, that's great. Whenever I upload things, I will make sure that you have the whole sheet. Okay, so let me share this app with you. Okay, so hopefully everybody can see my worksheet, and I will make it larger. Okay, everybody good with that? Everybody seeing what looks like introduction to limits. All right, I'm going to get the chat open in case you've got questions while we're moving through it. Okay, so here you can see I have a rational function. Okay, everybody good with that one? And if I factor it, and again, there are apps that do factoring, folks, so you don't worry about having to do this yourself. But just in case you're good with doing factoring, it tends to make things a little faster. Okay, and you can see this is a rational function. I have the same factor in my numerator and denominator, so I know I have a whole. Okay, and you might remember, okay, that this affects the domain of the function. Okay, domain means allowed values. Okay, and allowed means the values in the domain will give you a defined output. Okay, so I have to throw away 4 in my domain, because you can see if I plug in 4 to my function rule, I'm going to get a divide by 0 condition, right? So essentially, x equals 4 makes the function undefined. I'll call it f of x because that's what it's called. All right, and there's 2 ways to write your domain. You can write it with set builder notation like this. So it's the set of all x such that x is not equal to 4. Okay, and you can also write it in interval notation, okay, which says I can go from negative infinity all the way up to 4, not including it, or I can go from 4 all the way up to positive infinity. Here's the whole in between, okay? So these are 2 different ways to write your domain, okay? You've got, this is called set builder. All right, and this is interval. Okay, and you should be comfortable with both of those, hopefully, from college algebra. Okay. So again, what I would do is I would type this in, this function into my calculator, and then I would use a table feature, and it would give me values like this. Here is where I'm approaching 4 from the left. In other words, I'm below 4 and I'm approaching it from the left. Here's where I'm approaching 4 from the right. That means I'm higher than 4 and I'm coming down towards it, right? And here are the values. I'll just save you some time. Okay, so you can see, looks like I'm getting close to 6. Coming at it in the other direction, here's the largest number, that's 6.2. This is 6.1, and this is 6.01. You can see these are decreasing towards 6, right? And if you actually plugged in a 4, just like you'd expect, you would get an error because the function value is undefined. Okay, everybody good with it? And again, based on what you're seeing in the table, what do you think happens as f of x gets closer and closer to 4? Well, what happens to f of x? F of x gets closer to 6. Okay, that's what I would say based on what I'm seeing in the table. And if I were to graph this on a graphing calculator, this is what I think I would see. Oops, that didn't work out. Let's try it. All right, so here is my graph. Let me put some values here. Here's 4, here's 2. Okay, and I'm going to make this a little bit because I don't have a lot of room here. All right, so my graph kind of looks like this. All right, but right over here, there's a hole. Okay, so you can see that right when x equals 4, I get a hole. Okay. Okay. So again, question about table on a calculator. You want to do, you want to put the function in y1, y equals, right? Put the function in y equals. Then do second graph to see the table. Okay. If, like I said, folks, if you want me to do a one-on-one with you with the TI-84 and actually walk you through the process, I'll do that. Okay, but I would request that you ask me to do that separately from class time since the majority of students are not using a TI. Okay, remember you can graph this in Desmos as well, like I showed you. And again, just look to see what's happening at 4. Okay, you'll get the same graph. The only difference is here you can just go and click right on the 4, okay, the x equals 4, and see the undefined spot. Okay, everybody good with this? Anybody problems with it? Here's one I want to make sure you see, okay, and it is, so let's take a look at this one. This is more about the last one, okay? It says, does the graph drawn support your conclusion about the domain? Okay, and here's the question I want to address. Okay, the graph isn't linear. Okay, there is a hole at x equals 4. Okay, so I drew the accurate graph in the last picture. And again, you can see it does kind of support the idea that as I get close to 4 from the left, okay, I'm getting close to 6 on my graph, okay, and as I get close to 4 from the left, I'm getting close to 6 on my y value. Okay, so it does support what I said, okay, and what the table showed me. Okay. And again, you can say the limiting value as x gets to 4 from the left is 6. Okay, here it is with the the left-hand limit notation. I just want to make sure you see that. Okay. And again, the left, as x approaches 4 from the left, f of x approaches 6. And as it gets to 4 from the right, you also wind up with a 6. And here's the notation for that. Okay. So basically, you would say, since the left-hand limit and the right-hand limit match, okay, you could say the limit as x approaches 4. Notice there's no left or right here. Okay. No plus or minus, because the values are the same. Okay, so as long as the left-hand limit and the right-hand limit are the same, you can say the limit as x approaches 4 is 6, and you're good. Okay. Let me show you this interesting exponential function. Okay. This is sort of like a logistic function, which is used to describe limited growth. In other words, for example, if you have a population of bacteria, it grows almost exponentially. Okay, yes. Okay, question is, will the worksheet be saved in Canvas? Okay, so yeah, along with the video link. Okay, so basically you would look in Canvas under week 2, okay, where it says live online session video. Okay, it's in there, and then the shared documents are underneath. All right, so this is a logistic type function, and what it describes is, say, growth of bacteria for a while until they run out of food or space. Okay, so they grow exponentially, and then they run out of resources, and the growth kind of tails off. It becomes like steady state. Okay, it's an important type of function. Okay, for a lot of statistical applications. So let's take a look at this. Okay, you can do the same thing here. You can graph and look at table. Right? And again, I kind of did that, okay, on my TI. Right? And again, there are other graphing calculators out there that you can build a table from. At very worst, you can keep evaluating the function over and over again. Just go back and retype in the values for x that you want to check. Okay, so here's what I got when I typed in these values. Okay, so you can see what's happening here. Okay, as my x values get very large. Okay, this is pretty much okay. And again, remember the 11s aren't exact 11s, they're close. But again, I'm limited by the accuracy of my calculator. It only carries so many decimal digits after the decimal point. Okay, so as x gets large, my f of x value gets pretty close to 11. So I can say what happens as f of x, what happens to f of x as x gets large, and I could say the f of x values get close to 11. Okay. And again, it's kind of difficult. I know for folks, you tend to trust the calculator to be telling you the gospel truth, and it's not. Okay. This is a rounded number. Okay. And it's important to realize that. Okay? Because you're limited by the calculator's accuracy. Here's what this graph would look like. Okay, so let me see if I can graph my function here. Right. So here's f of x. To make the scale on this a little bit different for you to see it. So here I have 1 at 2, and then I have 6, 10, and 11. Okay. All right, so this function kind of looks like this. Okay, so you can see it kind of grows exponentially initially, grows very fast in here between 0 and 1, and then it kind of tails off and approaches a steady state value. Okay. One example of this might be, this could be a model for something like the amount of medication in a person's bloodstream. Okay, so as they initially take the dose, the amount of medication rises until it becomes a steady state value. Okay, you would expect it would drop off again after time, and then they'd have to take the next dose. Okay, so that's a kind of another example besides population growth. Okay. So if you look at this one, we can say here that we have a limiting value of our function as f of x tends towards infinity, right? Because we know this way, okay, toward infinity, okay? Now, infinity isn't a number. You're never actually going to reach that value, okay? But as x gets larger and larger, the value of the function is approaching 11, right? So again, what you want to notice here is the infinite limit. Okay, you can take limits at infinity, and that value will be 11. Okay, everybody all right with that one? Okay, and again, I already showed you when you approach a vertical asymptote, you're not approaching a limit, you're not approaching a number. Okay, so you don't have a limit there. So I just want to go to the summary page, and like I said, I will fill in the rest of these for you. Okay, but we'll run out of time if I try to do them all here. So I'm going to fast forward a couple of pages and just make sure you have some summary information. Okay, so what have we learned or recalled? Okay, well, a limit at x equals c doesn't depend on the function value. Okay, we learned that. Okay, so in other words, the function doesn't have to be defined at c, and we can still have a limit. Okay, what are the different ways we learned? Okay, we learned graph f of x and observe values of f here. Okay, that's one way to do it. Another way is look at a table of values. And we also looked at, you can evaluate a limit algebraically. Okay, and of course, algebraically implies that you remember some algebra. Okay, like we did factoring a polynomial, or maybe in the case of square roots, rationalizing a denominator, and so forth. Okay, here's kind of the takeaway. Okay, the concepts to understand. Okay, if f of x gets large or small, outbound, as x approaches c, then the limit as x approaches c of f of x, dne means does not exist. Okay, so if the function values are growing towards infinity, okay, this is the vertical asymptote case. Okay. So basically, if you then have this, if the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x, then you can say the limit as x approaches c, no plus or minus, okay, equals whatever the value is. Okay, so I guess I should have done that. Let me just say this. And let's say it's some number n, okay? The two limits match and it's n, then you can say the limit as x approaches c is n. Okay? If this last situation isn't true, then the limit doesn't exist. Okay, the limit as x approaches c of f of x does not exist. Okay, so the important thing to pay attention to here is be able to tell what a limit is and be able to tell when it doesn't exist. Okay, so vertical asymptotes, for sure your limit doesn't exist. Okay, and then holes, okay, most times your limit exists there. Okay, because you're approaching the same value from the left and the right hand side. Okay, this makes sense? Is this okay? This is kind of a summary of limits. Good? All right. In the very short amount of time we have left, I'm going to talk about continuity. Okay, and it turns out once you understand the idea of a limit, okay, continuity is really, really simple. Okay, so let me go back here. Continuity is just another way of saying for every point that you're interested in on the graph, okay, it's friendly, okay, it doesn't have any breaks, okay. The way I like to tell students is the informal definition is, okay, you can draw the graph without lifting your pencil. Okay, and that means it's continuous. Okay, you can draw the graph without lifting your pencil, that means it's continuous. Mathematically speaking, okay, here's what it says. A function f is continuous at a given x value if and only if the limit as x approaches that x value is the same as the function value. Okay, so think about what that means. That means no holes, okay, no jumps, okay, because then the limit wouldn't exist, right? Okay, so it's important to understand, again, function values that are going to be continuous. Okay, you might remember from college algebra that most functions are continuous that you've played with. Polynomials are continuous. There's no holes, no jumps. Okay, there are what other functions are continuous? Exponentials are continuous. Log functions are continuous. And I'm not talking about functions that have an entire part of their domain, you know, that are excluded, like logs or square roots or whatever. What I'm saying is there's no holes or jumps. Okay, can anybody tell me what family of functions has jumps in it? What function family has jumps in it? Where all of a sudden you're going along and whoop, then the function value jumps way up. Anybody remember what they're called? Okay, do you remember this family? Piecewise. Okay, piecewise functions. They're ones where you have a different domain for different parts of the function or different rule for different parts of your domain. Typically, piecewise functions are defined on all real numbers, but there's different output rules for different parts of the domain. These are used in business a lot for pricing structures, okay? Up to so many gigabytes, here's your pricing rule. Above that number, here's a different pricing rule. Maybe we charge you at a higher rate, okay? So that's kind of a function. So the functions that tend to not be continuous, okay, non-continuous functions tend to be either rational with holes, okay, or asymptotes or piecewise. Okay, non-continuous functions that we're going to be dealing with are usually going to either be rational or piecewise functions. Okay, so it's important to be able to recognize those. Right? So here are some ways functions can behave near a particular point. Okay, and you can look at this graph and the table here to get an idea of what we're talking about. Okay, you can see as we get close to x equals 1 from the left and from the right, the function value is approaching 2. That's also what the function value is at x equals 1. So this function is continuous at x equals 1. Okay, now if you look at 2 over here, we've got a hole. Okay, as I approach it from the left and I approach it from the right, the limit as I approach x equals 2 is 2. That's fine. The limit is great. But what's the function value there? It's 1. Okay, and it's not the same as the limit. So that shows you you've got a discontinuity, namely a hole. Okay? This is called a removable discontinuity, okay, because you can change the value of a single point. You can make the function continuous just by changing the value of a single point. Okay. Other types of discontinuities, like this one, okay, you can see as I approach x equals 3 from the left, okay, I'm approaching the y value 2. As I approach x equals 3 from the right, I'm approaching the y value 1. Okay, this is called a jump discontinuity or a non-removable discontinuity. There ain't nothing I can do to this because this is essentially the part of the rule that's defining this and the part of the rule that's defining this. I can't, without fundamentally changing the function, I can't get rid of that. Okay. And then the same thing is true of a vertical asymptote. Those are not removable discontinuities because it would take a major overhaul of the function to make them go away. So really the only removable kinds are the ones where you've just got one point out of place. Okay? So again, this function is continuous at x equals 1. It has a discontinuity at x equals 2 and another discontinuity at x equals 3. And here's another hole, another discontinuity at x equals 4. Okay? Everybody kind of all right with that? Anybody have any questions about what I mean by continuity? All right. And again, you can see easily if you were to try to draw this red line, you would not have to lift your pencil to go through x equals 1. But you would have to lift it here to make the circle and to put the other point down here. Just likewise, you'd have to lift it here to get the jump into the function. Okay? So everybody is comfortable with that, I'm assuming. Intuitively, it's important to understand what we're talking about. Okay? Okay, so basically every function you've studied is continuous where it's defined, okay? Polynomials, radicals, rationals, exponentials, okay? But basically you've got discontinuities in rationals, you've got to pick them out, okay? And then the piecewise functions tend to have discontinuities at the ends of the domain. Okay? So what I'd like to do in the time we have left, I want to just go back to the worksheet we were using. And hopefully we can talk a little bit about continuity. And I want to talk about the piecewise functions. So let me share that with you. Okay, so hopefully you're seeing my worksheet here. Let's see. Okay. So here's the way piecewise functions are defined. Okay, you might remember these from college algebra. Okay, where you've got one function rule defined on part of the domain. So in this particular example with number 1, okay, I've got a quadratic as long as x is less than 1. And then if x is greater than or equal to 1, I have a linear function. Okay, you can see there's a huge jump right here. Okay, and essentially this limit as I approach x equals 1 doesn't exist. Okay, so the limit as x approaches 1 of this function does not exist. Okay, is everybody clear on why this limit doesn't exist? Because as I travel along the function from the left, I'm approaching, as x approaches 1 from the left of f of x, that's getting close to 4. And the limit as I approach x equals 1 from the right of f of x, I'm getting close to what looks like negative 0.5. Okay, so the two left and right hand limits don't match. Okay, so as soon as I know the limit doesn't exist there, I know I have a discontinuity. Okay, so if I want to describe the interval on which each function is continuous, I have to leave out 1. So I would say I can go all the way from negative infinity up to 1 and not including it. Now, technically speaking, okay, if I look at the way they've drawn the graph, okay, you can see that the solid dot at 1 is included in the second part of the graph. Okay, so I can say that I am continuous from 1 on out on that left-hand part of the graph. Okay, so those are the intervals where the function is continuous, and I just have some weirdness right at 1. Okay, does everybody understand how I got this? Okay, with example 1. Right? Yep. Okay. Let me show you, in case you're not familiar with it, how to graph this function on Desmos. Okay, and that'll pretty much take us to the end of our period. Okay, the rest of these are just more and more examples, which I will do, and I will upload with our video so you have them. Okay, so let me make this smaller. Okay, and here's Desmos. I'm going to get rid of this. Let me show you how to graph with a restricted domain. Okay, so I have a piecewise function, and it has this rule, x squared plus 2x plus 1, but it's only for where x is less than 1. So here's how you restrict the domain. You use curly braces, okay? And then you say x is, and you want to use less than. Okay, less than should be on my keyboard here. Oops, my bad. And then you have the closing curly brace. Okay, so you can see I got just that part of the curve, right? And again, if I want to draw the second half of the rule, which says x is or y is negative x over 2, all right, and I want to restrict that to where x is greater than or equal to 1. Okay, and let me get that out. Everybody see how I did that? It's super, super easy. You're just using the curly braces to put the domain statement. Okay, and you can see again how this works, right? You should be able to see over here, you've got undefined, but over here you've got a value, okay, for x equals 1. Okay, so here's where the value is. Okay, everybody okay with graphing a piecewise function in Desmos? Okay, everybody good with this? Okay, and again, the reason why this has a discontinuity at 1 is because the limit doesn't exist there. Okay, remember, 2 different left and right limits. Okay, I would wind up with a discontinuity at a whole as well. Okay, because again, the limit would exist, but it wouldn't be equal to the function value. Everybody all right with that? So continuity at x equals c means limit as x approaches c must exist. I am having trouble typing English. And must equal the function value. All right, so here's what I put in the chat. Continuity at x equals c means the limit as x approaches c must exist and it must equal the function value there. Okay. So that's kind of a summary of limits and continuity. And hopefully that's clear to folks. Okay, so what I am going to do is I'm going to stop sharing. Okay, and go back to our meeting. Okay, and let me ask any questions on anything. On limits or anybody have any questions on limits or continuity? Now again, if you are struggling with your particular method of graphing, if it's not Desmos and you want some one-on-one help, just send me an email in Canvas and we can set something up. Otherwise, I'd strongly encourage you to use Canvas as much as you can because it's much easier to use. All right. But that's all I have for today. So I'm going to stop my recorder